Hi guys. All right, we're back to the wind and weather maps, and it's going to get interesting. So you might have to watch this one a couple of times. This is pretty big. So we're going to start. I've already got some diagrams here for you. We're going to start by way of review. So I'm going to move this over here. And I want you to tell me what direction are the winds at letters A, B, C, D, and E. And I want you to think about what it would be if it was mesoscale and what it would be if it's synoptic scale, okay? So at letter A, then you should stop this and figure this out. So write down your answers. Tell me how you're doing. Letter A, what do you think the winds are if it's mesoscale? Now, I'm hoping that you say that the first thing that you think about doing is drawing the arrow that represents the pressure gradient force. And remember, it should be this way. Did you get that? I want you to see these isobars. This is 500 millibars. This is 490. So there's a pressure gradient here of 10 millibars. And it is going from high to low pressure, perpendicular to the isobar. So that's this way. So if it's mesoscale, the air travels according to the pressure gradient, and so the winds would be out of the northwest. At letter B, they'd be out of the north. Letter C, they'd be out of the northeast. At letter D, same thing, out of the north, and E is like A, out of the northwest. Okay, but here's the thing. What is the wind doing if this is synoptic scale? So the first thing I want to do is, when I go to synoptic scale, I want to think that there is a Coriolis force that goes opposite. So we're going to assume that all of these winds are trying to be geostrophic, which is a good assumption. If anybody knows anything more about meteorology, it's not perfect when it's curving, but we're not going to worry about that for this class. And then the winds are going to want to go this way, but they get turned to the right, which means they're this way at letter A. They want to go from this direction, but they get turned to the right. Now remember, this is the right based on where you were going. Okay, you were going from north to south, so if your car is driving southward and you turn right, now you're heading westward. So this wind is going to be from the northeast. This wind is going to be from the east. This one is going to be from the southeast. D is going to be the same way. It's from the east. And letter E, remember, it wants to go this way, but instead it turns to the right. Okay, so that's the direction of the winds in the black arrows. Now the question is, what is the trough? Is the trough letter B or is the trough letter D? So I'm going to do this for a second. I'm going to remove those, keep this out of my way. What is the air doing over here at letter D? Remember, the air is moving this way. I'm going to go ahead and use a different color, just like the air is moving this way. And which way is it curving? It's curving. If I kept going around this way, right? Which way is that moving? Oh, that's a terrible arrow, but you get the idea. It's moving this way. And that would be curving clockwise. And clockwise in the northern hemisphere is anticyclonic. So where is there an area of high pressure? The area of high pressure is right over here. And therefore, this over here, this little axis here, letter D, that's the ridge. So what's over here at letter B? Same thing. The air is traveling. I'll go back to green for a second. The air is traveling this way, which if you followed it around would be going counterclockwise. And so this is a big low pressure area. There's where the cyclone is. Okay? So this axis here is the trough. So the trough is at letter B, the ridge is at letter D. Notice the trough is upside down. You don't want to think of the trough as being the bottom. You want to think of the trough as where the air curves cyclonically. You probably ought to write that down. And so this is a backwards wave. Notice that the overall wind in this region is blowing from east to west. So it's what we call an inverted trough, because it is different than what your brain thinks it. You need to remember that a trough is an area of low pressure where the air curves cyclonically. And that is how you need to think of that. Okay, so we're going to undo these things. And I'm going to go to this picture. Now we need to think differently. Okay, so the first question is, what is this hatched line? That's the ground. That's the surface. And so what I'm imagining here, and I'm kind of doing it in 3 dimensions, is I'm seeing a plane that's parallel to the ground. Now the ground doesn't really look like it's 3-dimensional. So really what I want to do is I want to think of this as being in 2 dimensions. So I see a line here, and this line I am going to label as, ooh, not that large, I'm going to label this line as 1,000 millibars. And so the question is, what is that solid line? Now, I'm sure most of you would say, well, it's an isobar. An isobar, iso is a prefix that means the same. Bar refers to like a barometer, measures pressure. So you'd say, well, that's a line of constant pressure. Okay, but that's not what that is. That is a cross-section of an isobaric surface. So I'm going to write that in here so you have it exactly what you want. Section of an isobaric surface. And in this case, you can kind of think of that as a plane. Okay, and so what I want you to do is think about this. I want you to see this little picture. This is a plane. Oh, I don't know if you can see that with this background, but there's the plane. If I turn it on its side, do you see that you're really only seeing the edge of that plane? Not this, you're seeing the edge of the plane. And that's what this line is all about. You are seeing the edge of a plane that goes parallel to the ground. Okay, so what do I mean by that? When I have a map view, so here's a map view. And in this map view, what I'm saying is that this is north. And I think I've already I did this with you the other day. That's north. Okay, so when I draw a line on this map, and I call that line 1,000 millibars, do you agree that we're saying that's an isobar? On one side of the line is less than 1,000 millibars of pressure, and on one side it's more than 1,000 millibars of pressure. Now remember, air pressure is defined as the weight of the air above you. You need to go review that. We have talked about this. Okay, so 1,000 millibars. One side of the line is under 1,000, one side of the line is more than 1,000. So if I walked on this line, right, and if I walked on it, my feet would be standing on this surface, on this box, and I'd be moving this way. I'd be moving to the northeast, let's say. One side would be less, one side would be more. But if I go over here to this image, and here's going to be kind of silliness, if I stood on this plane, which way would I stand? And the answer is, I would stand like this. So if you'll excuse me while I make a silly drawing, and I'm walking this way. Okay, I'm walking on that line. Now remember, I'm not doing a tippy toe. I'm not balanced on a wire because it's a whole flat surface. I could move left or right. So as I move, and I don't know if you can, I always get confused whether you see me on Zoom when I have the whiteboard up. I don't think you do. But what I'm imagining is a plane. And if I walk left or right or this way or backwards on that plane, every place on there is the same pressure. That's why we call it isobaric, all the same pressure. But then here's the question. Is there a pressure gradient on it? And I'm like, well, I don't know. Remember, pressure gradient is a change in pressure as I go from here to here. But if every place on the floor, on this plane, is 1,000 millibars, then there's no difference in pressure And if there's no difference in pressure, I don't have a pressure gradient. If I don't have a pressure gradient, I don't have a wind. So I'm just walking on the floor and there's no wind, okay? So let's go back and think about this for a second. So I'm gonna remove this person. Oh, there goes my arms, legs, lost my head. And I'm gonna go up here and say, all right, what is this line? And you'd have to say that's a cross section of an isobaric surface. Okay, what do I mean by that? What pressure would it be? Well, if I'm down here on this surface and it's 1,000 millibars of pressure and the weight of the air above me is pressure, then if I go higher, I'm going to be less than 1,000. So in this case, let's imagine 500 millibars. Okay, so over here, I have 500 millibars of pressure. Now, just to show you, to get you thinking a little bit better, how much air do I have between those two isobaric surfaces? And I bet you don't know what you want to answer. I want you to try to answer that question. So right now, on your notes, write down the answer you think. How much air is in between those two isobaric surfaces? So I'm going to show you a picture of me. I'm saying here's those two isobaric surfaces. How much air is in between them? What do you think the answer is? Some of you might say 500, something along those lines. Here's the thing. What if, and this time instead of drawing the whole person, I'm just going to draw my head. Okay, what if I'm standing there? How much air is above me? Now you could say above me, that's my head, is 1,000 millibars. But really what you should say is how much air is above me when I'm standing at the ground? The answer is all of it. Okay? When I'm at the ground, how much air is above my head? All of it. All of the atmosphere is above me. And how much is that putting pressure on? About 1,000 millibars worth. So if my head, rather than being there, what if I put my head here? Okay, now how much air is above me? Well, you could say 500 millibars is above me. So how much is up there? Half. If all of it is 1,000, half of it's 500. If that's the case, then what I'm saying is that how much air is in this layer? You'd say about half of it. Okay? So we're going to understand that we're looking about half the atmosphere. Now, if I want to show you something over here, so I'm going to hide this just for a second. I'm going to open a new window and we go cross-section pressure atmosphere. Okay, I just do something like this and I can look at an image and I'm even going to go this one. I think this one works for me. Okay, notice that down here it's 1,000 millibars. Up here it's 500 millibars, and they're saying that's about 6,000 meters. Okay, so that's kind of interesting, but notice that for every 2,000 meters, I'm going down by more pressure. So if I look at pressure like this, and I think we did this in class. Oh, this is not what I want. Pressure, let's do this. Pressure, height, atmosphere. I see pressure decreases, do you remember? Exponentially. So I've got this exponential decrease. So 500 millibars here may be way more up here because it's higher up in the atmosphere. The atmosphere is getting lower pressure exponentially. And the reason for that is the air is becoming more and more expanded. So I want you to imagine this. If I take a box of air and I lift it up, now we've said this before, what's the first thing that happens? First thing is that the pressure decreases. The box expands and the temperature cools by 10 degrees Celsius per kilometer. Now, how many times have I said that? Do you think I want you to know that? I'm thinking the answer is yes. Drink some iced tea. Yummy. Okay, so when a box expands, do you understand the volume is getting bigger? Now this box, this parcel, I like to call it a Vegas box. Because what's in Vegas stays in Vegas. What happens in Vegas stays in Vegas, right? So what's in the box stays in the box. So I've got some amount of molecules flying around inside this box. When I lift it, it gets larger. Now the number of molecules is staying there, but they take up more space as the box gets bigger. So what we're saying is that the air becomes less dense, okay? And that becomes less dense because the pressure is going down. But here's something else that's interesting. Imagine that I have this box of air and I heat it up. I put it on the stove, or I put, like in a balloon, I put fire underneath it. You understand that making it hotter is going to cause it to expand also. So what causes the air to expand? Pressure goes down, the air will expand. But if you make it warmer, the air also expands. Okay? So I want you to think about that for a second. Heating the air makes the air expand. Making it expand makes the air less dense. Okay? So let's go back to our picture here. And we'll go ahead and put the on here. I'm going to look at a picture and I'm going to do something a little bit different. And now I'm going to draw something that looks like this. Okay? And I'm going to say this is 500 millibars. Now, over here, if I drew my head, here on the bottom, how much air is above me? And the answer is all of it. And we said, how much is that? 1,000 millibars. And I could draw my head there, or I could draw my head there, or I could draw my head there. If I were in class with a marker, I'd draw an entire person, but there you go, you get it? So now the question is, well, how much air is above my head if I'm over there? And then you should say, well, there's 500 millibars above me. 500 millibars worth. What if I drew my head over here? Well, I've got 500 millibars of air above me. My head's a little bit rounder here and a little bit squished over there. But what if I drew my head, and this time you gotta watch this, I'm gonna draw a horizontal line, and I'm gonna draw my head over here. Over here, there's 500 millibars above my head. But how much air is above my head here? And the answer has to be more than 500 millibars because I have 500 millibars of air above me from there. But here to there, I've got some amount of air between my head and that 500 millibar isobaric surface. So my pressure, as it turns out, is going to be higher over here. I've got higher pressure there, and what's my pressure over here? It's 500 millibars, and I'm going to put an L over there for low pressure. Okay? And what that says is when I go from here, the pressure is, I don't know, 600, 700 millibars. But if I walk on this horizontal plane all the way over here, the pressure gets lower. So what is this blue arrow that I'm drawing supposed to represent? Oops, arrow. What does that blue arrow represent? The answer is, that is the pressure gradient force. The pressure gradient force says the air wants to travel from high here to low pressure over there. So I'm going to go from this, where this is where my head is, and now I'm going to roll my head, and I'm going from a higher pressure to a lower pressure. That's what way the air wants to travel, from high to low pressure. Now, that's a cross section. See, this is a little bit different, but it still shows you that this yellow line represented a horizontal plane where the pressure on one side is greater than the pressure on the other side. And now I've got this pressure gradient force that exists. Okay? So before we go beyond that, let's ask a couple of important questions. Okay, so first thing is, why is this distance from the, let me use a different color. Why is this distance from here to here different than this from there to there? Now, do you agree that between these two isobaric surfaces, there's 500 millibars worth of pressure over here, half the atmosphere? What about over here? Well, half the atmosphere. So why are they further apart? Okay, now I'm going to go back to having you take a look at me. Here's the layer of atmosphere. Here's 1,000 millibars, that's the bottom, and here's halfway through the atmosphere, 500 millibars. Well, what would make it on, basically when you're looking at it to your left, it's smaller, and to your right, it's greater? Well, what do you think makes the difference? The answer is, it's the temperature. If I take a box of air and I make it warmer, what does the box do? It expands. Well, what if I took a layer of air and I warmed it up? Do you agree that that layer of air would get further apart? So what I'm saying is that over here on this side, the temperatures are warmer. And over here, they're cooler. Because this is further apart than over here. That layer has expanded. All right, so what I need to do here is I need to write you something, and I'm going to say this is known as the thickness relation, which says the vertical distance between two isobaric surfaces is directly proportional to the average temperature of that layer. The vertical distance between two isobaric surfaces is directly proportional to the average temperature of the layer. In other words, the thicker, the warmer, and I probably should put a comma in here because I'm writing it now. The thicker, the warmer, the thinner, the colder. And I'll try to spell other correctly. Okay, so watch. If it's warmer, it expands, and the layer is thicker. If it's colder, it contracts. That means the layer is thinner. Thicker the warmer, or actually the warmer the thicker, and the thinner it is, the colder that must be. So that vertical distance in this thing called the thickness relation says the thicker the warmer, the thinner the colder. Now listen to me. On a test, I'm going to probably say the thicker the warmer and a space. And then what do you say? The thinner the colder. I had a student always said, that's not a question. I'm like, we said this in class a dozen times. Thicker the warmer, the thinner the colder. The thicker the warmer, the thinner the colder. The thicker the warmer, the thinner the colder. You should say it 3 times. Okay, so when I see isobaric surfaces like this, and they're further apart, I know it must be warmer. And over here, where they're closer together, it must be colder. Okay? Now, I'm going to do something a little bit different. I think I'm going to keep most of this, but I'm going to undo the text because I don't need everything here. I want to think about something. Do you agree that the pressure, I'm even going to take away a little bit more. Take off my head, there we go. Did you know that the pressure here at the tail of the arrow is 1,000 millibars? And over here, it's 500 millibars. So if I took air and I said, I'm going to take a parcel of air like this, what does this parcel want to do? Well, just because it's vertical doesn't mean anything. Remember, this way is up. So what does that box want to do? That box is air. It wants to move from high to low pressure. So that box wants to go upwards. Woohoo! Now, do you remember in geostrophic, there was a balance between air wanting to go horizontally, sideways, from high to low pressure, and there was a force that went the opposite way. What was that force called? That's right, the Coriolis force. That's called geostrophic. But in this case, the air wants to go up. Well, gee, I wonder if there's a force that acts opposite the pressure gradient force. Oops, that's not what I wanted. I wanted an arrow that acts opposite the pressure gradient force that makes the air want to go down. Well, what makes anything want to come down? The answer is gravity. So over here, I have gravity wanting to push the air down. And over here, I have a vertical pressure gradient force wanting to push the air up. The balance between those two forces is called hydrostatic. And that's just something I want you to know. That's the name of it. Hydrostatic is the fact that air wants to go up because it's lower pressure, higher up. There's less air above me. The gravity keeps it back down, and there's always, at least there usually is a balance, and air doesn't want to go up or down, it just kind of stays there. And we're going to see that there is something that makes it want to go up or down besides those two forces. But for now, just understand that there's a vertical balance of forces called hydrostatic. Pressure gradient force up, gravity down. Those two balance called hydrostatic. There is a horizontal balance of forces. One of them is pressure gradient force, one of them is Coriolis. When those two forces are balanced, that is what we call geostrophic. Okay? So in your notes, and this is going to be so important that you go rewrite these notes and work it out. Work it really hard and make it great, because that will help you understand it and process it very well. So one last thing in today's lecture, and let's see if we can put a couple of concepts together. Okay, so I'm going to take this out. I can just undo this here, and I'm going to draw a letter, and I'm going to draw this at letter A. I can make it a little bit bigger. So there's letter A, and here is letter B. Okay? Now, first question is, what's the pressure at letter A? Try to answer those questions before you listen to me. So pause this, think about the answer, right? If you were in my class, I wouldn't let you just listen. I want to engage your brain. So what's the pressure at letter A? It should be 500 millibars. What's the pressure at letter B? Well, it's between 500 and 1,000 millibars, so more than 500. Do you agree that this arrow represents the pressure gradient force? The air wants to go this way. When does the air travel toward low pressure? The answer is on the mesoscale. Okay, so watch this. This is, I think this is the way you'd see the screen. Right? Let me see. You're going from B to A. And you're walking this way. I think that's how you see it then, right? Meaning I'm going from letter B to letter A. But what if this is synoptic scale? What if this is large scale where the Coriolis force does? What does the Coriolis force make you want to do? It makes you want to turn to the right. So it goes away from me. Do you understand that if this is geostrophic, the actual wind is into the page? And it's hard to draw that because it's three-dimensional, but you have to imagine that the air is trying to blow into the page. So at this dot right there, if it were mesoscale, the air is blowing from B to A. If it is synoptic or larger, global scale, it's going to go not, it wants to go from B to A, but it's going to turn right and go into the page. So you have to understand how those frames or how those winds are able to be determined based on where you're standing. Where's your frame of reference? Okay, on the cross sections into the board. So that's kind of interesting. But if you imagine this, imagine that you're now a person walking into this plane. So here's my, oh, that's a really thick head. Don't make a comment about thick heads. I know what you were thinking. Here's my head. What color should my head be? I'll put my head black here. Here's my head. Okay. Here's my body. This time I'm going to draw the body. Okay. Oops. Legs, legs. My arms are here. Okay. Which way am I walking? I am walking into the board. I'm walking into the screen, which means which way is my left? My left is that way, right? That's the left of me. And guess what I'm pointing to? Letter A, where the pressure is lower than at pressure B. So the Bayes battle law says with the wind at my back, low pressure is to your left. So the wind's blowing into the page, and I point to the left, and that's where I'm pointing to letter A. I'm pointing with the pressure gradient force. So what would the Coriolis force look like? Well, the Coriolis force is opposite. Oops, I didn't draw an arrow. Is opposite the pressure gradient force, and the air is blowing into the page. So that's really important. Now we're going to eventually talk a little bit more about how the temperature changes create this. We're going to get into what's known as the thermal wind. And you're going to see how all of this kind of fits together. So we've got one more lecture on this. But man, is this an important lecture for you to wrap your head around. And if I need to add more lectures to help you out, I will do that. But this lecture should be pretty good. You might have to watch it more than once because it is difficult. And guess what I'm expecting you to do? I'm expecting you to use your brain and to get an A. And to get an A, you have to fully understand what's going on. So if you're confused, go back and watch it again and stop at a point, little points in time, and figure out what I'm saying. If you still don't get it, then you need to come talk to me or we'll do a virtual office hour, okay? But that's what's going on. So I can stop sharing my screen. Oh, that's not what I'm doing. Stop sharing my screen. And that should be the end of today's lecture. So that one, I'm really going to look for a great set of notes. So figure it out and feel free to write on the discussion board about questions, share with each other. I always wish we had groups. I'm not a big fan of online learning, but it's what we have this summer, and it gives you an opportunity to figure out what you want to do. Okay, guys, I hope you all do well. Have a great rest of the day.